Consider stochastic gradient descent. We want to minimize a loss function f based on some given data. At each time step, we choose a data point gamma of n to approximate the direction of steepest descent. We scale the sampled gradient by a learning rate h and update our approximation for the minimizer xi accordingly. Looking at a realization, say for minimizing the least squared error in a linear regression, we may get the idea of approximating SGD by some continuous process, say one that satisfies a differential equation. By identifying the continuous time point t with n times h, this is accomplished by the evolution of the mean negative gradient, also called gradient flow. This ODE is widely considered to be the continuous time analog to gradient descent, whether the latter is stochastic or not. However, this approximation does not capture the stochastic nature of SGD, so we may add a further diffusion coefficient to arrive at a first-order diffusion approximation, also called a stochastic modified equation, or SME for short. The diffusion coefficient incorporates the learning rate h and sigma, which is the variance of the sampled gradient. It may seem strange that h appears now in the approximation, when usually we may think of letting h converge to 0. But one should keep in mind that we are using this approximation trying to understand SGD, which has a relatively small but still positive learning rate that needs to be chosen. Of course, any single realization of SGD and the SME may be very different from each other. However, the processes have similar distributional properties. Assuming some technical linear growth, Lipschitz and smoothness conditions on the gradient of f, its expectation, and the matrix root of sigma, we can prove a precise weak approximation result. For all smooth functions g with derivatives of polynomial growth and a positive time horizon t, the distance between the expectation of g applied to xi and g applied to the solution of the SME x over all discrete time points is converging to 0 linearly as the learning rate h goes to 0. Because this is a mouthful, with regard to the distance we will simply think of g as a squared loss and consider the distance between the loss of xi and the loss of x. This approximation result for the first order SME has previously been proven by Li, Tai and E. By looking at the proof, it becomes clear that the same result also holds for gradient flow, not just the first order SME, which begs the question, what sort of advantage is really provided by adding a diffusion component? This brings us to our first main result, the first order error expansions. Both gradient flow and its diffusion counterpart are first order approximations of SGD. However, we can actually characterize the error more directly. Given the aforementioned assumptions, a fixed initial condition and learning rate h, the difference between the losses of xi and x is given by h multiplied by the time integral of a function phi applied to gradient flow from 0 to t plus some second order remainder term, where for gradient flow phi is given by a somewhat lengthy expression depending on nabla f, sigma, and the second partial derivatives of the loss of x, when we start x at time little t and evaluate it at the time horizon capital T. We will call this loss y. In the diffusion case, this changes so that sigma disappears from phi and reappears in the dynamics of x. Let's sketch the proof of this result, in the gradient flow case for simplicity. The Feynman-Katz formula implies that the derivative of y with respect to the initial time minus the inner product of nabla y with nabla f vanishes. And also that at the time horizon t, y is exactly g. Then we can express the difference in losses using a telescoping sum and then apply a second order Taylor expansion to y. The second order terms match exactly our definition of phi, and the first order terms vanish thanks to the Feynman-Katz formula. In the next step, let's look at this remaining sum over the expectation of phi at k times h applied to xi k. We want to replace this with the integral of phi of x, which means we have to make an estimate to go from xi to x and from the sum times h to the integral. Both estimates tell us these additional terms are all of order h squared at worst, leaving us with the desired result. In our linear regression example, we can see that phi is, in absolute terms, truly smaller in the diffusion case, and therefore adding the diffusion coefficient to gradient flow gives us a better approximation to SGD. So far we have only considered a fixed learning rate. Let's see what happens if we vary it over time. For example, we could decay h by multiplying it with 1/1 plus the current discrete time step. Accordingly, we extend our definition of SGD by incorporating the term u of nh, where u is smooth, constant or strictly decreasing, and takes values between 0 and 1. We can now reinterpret h as the maximal learning rate. U may also depend on h. This would actually be necessary in our example as ut equals 1/1 plus t over h, and will also generally be important for, say, deriving an optimal learning rate schedule for SGD using the SME. Everything still works out as long as u has bounded derivatives in h. If we then change gradient flow and the SME by multiplying the coefficients with u, the previously derived error expansions still hold, at least after modifying phi for both equations. Now, we can find approximations which are better than first order. By adding an h-dependent term to the drift coefficient of the first order SME, we can derive a second order diffusion approximation, at least in the case of constant learning rate. The previous approximation result improves so that the error converges now to 0 quadratically as h goes to 0, which again has been shown by Lee, Tai, and E previously. However, what second order SME would we get for a time-dependent learning rate? Of course, we need to multiply the coefficient somehow with the decay function u, but what is perhaps surprising is the appearance of a new term involving the time derivative of u. This is our second main result. In order to derive this equation, we can start with a somewhat generic candidate x for a second order diffusion approximation with drift coefficient b0 plus hb1. We can use a stochastic Taylor approximation for the expectation of the one-step difference of x. By one-step difference, we mean the value of the process at time n plus 1 times h, if it started at n times h, minus the initial value. We want to match this expansion with the expectation of the corresponding one-step difference of xi, which is defined similarly. In order for these to be as close as possible, evidently, we should first set b0 equal to minus u times nabla f. Then we want the h squared term in the stochastic Taylor expansion to vanish as well, implying b1 should be equal to minus a half the Jacobian of b0 times b0 minus the time derivative of b0. By comparing the second moments of the one-step differences, we could further deduce that square root of h times sigma is the diffusion component for our second order SME, giving us the full equation.